gonna look at section 5.3 first, and this is on the definite integral. That's the very first thing we're gonna start out with here is the definition of that. So we are going to let f of x be a function as per the usual, and it is defined on this whole interval from x equals a to x equals b. So it's never undefined in that region. And then we can define the definite integral of that function by using a Riemann sum. Okay, so remember our little integral symbol. We saw this back in section 4.7, I believe. Integral symbol looks like this. Okay. And this definite integral involves the endpoints of your interval. So from a to b, how we write that on the integral symbol is like this, a to b. Okay. And then we have f of x dx. Okay. So how this is actually defined is that it is the limit as n goes to infinity of a Riemann sum, which is the thing that we talked about last class. That was our summation from k equals 1 to n, f of ck times delta x. Okay, so that is the Riemann sum part of things. All right. And now to get into a little more detail on what's going on here, we're going to look at the integral notation. Okay, so that's this side of things, a to b, f of x dx. All right, so again, the swooshy stretched out S type of symbol there, that is the integral sign. We do need one of those to show that we're taking an integral. A and B are called the limits. A is the lower limit of integration, and B is the upper limit. So yeah, together A and B collectively are called the limits of integration. Okay, so we have those. And then f of x, I think we discussed this last time we saw the integral sign. The stuff inside your integral is called the integrand, thing that is being integrated. And then x here is the variable that we're doing things with respect to, all right? And we call that the variable of integration. So one kind of interesting thing about the variable of integration is it's almost just like a placeholder, and we'll see really a little bit more about that in this section, the homework on that, and in section 5.4. The fact is we could use any variable here and this integral would still turn out to be the same thing. So could use any variable here. All right. It's called, when we do that, it gets the name of a dummy variable, like it's just a placeholder type of thing. Okay, so whether we're integrating from a to b f of x with respect to x, that's the same thing as integrating a to b if you did like f of t with respect to t. As long as the variable matches inside of there, like x dx, t dt, it's still going to be the same result. Okay, kind of like with derivatives, as long as the variable that you were working with respect to matched the variable in the function, the derivative would still turn out to be the same thing. Okay, so you could put literally whatever you want. Theta, d theta, it doesn't really matter. All of those turn out to be the same result. Okay, so that's a little detail on this side of the definition. And then we'll just briefly recap what was going on over here with the Riemann sum. Okay, so for the Riemann sum, we're going to use the kind of default Riemann sum that we set up at the very end of last class. So we use the default Riemann sum from section 5.2, last few pages of those notes, where there are n equal width rectangles and the default for those points in here, the C sub k's, those with a general Riemann sum, those could be like left endpoints, right endpoints, midpoints. But our default setting for that we talked about was to use the right endpoints. Mathematical tradition there. Okay, so the CK are the right endpoints. Okay, so from that we had kind of a little formula that we had come up with at the very end of class last time, where we could get the width of each rectangle, that delta x, by taking the length of our interval, so that's the difference between A and B, and cutting it up evenly between n equal rectangles. So that was the b minus a over n thing that we did last time. And then we had also come up with a really general formula to find the right endpoint of any rectangle. So this is CK, the right endpoint of the kth rectangle, where k is like any number there. And we had done that by going a plus k times delta x. But we see that delta x is b minus a over n, so a plus k times b minus a over n. Okay, so those are like our default settings here, and we'll use that in our integral definition. Okay, so there's our details on notation, what we're actually doing in that equation up there. And now some conditions for this to work. Okay, so it is possible for us not to be able to get an answer out of this. It's possible for this definite integral to not exist. All right, and one key thing to notice with that is that there's something else in this equation that we use those words does not exist a lot with. We often, when we were looking at limits, we would find that certain limits don't exist. So if this limit on the right-hand side doesn't exist, then our definite integral cannot exist. So that is important to keep in mind. So the limit of our Riemann sum must actually exist for the definite integral to exist. Okay. So yeah, the right-hand side of the equation has to work out and exist for the left-hand side to exist. Boom. With the Riemann sum, another thing we can say for this existence that you might see, this is a really common term in calc too. So just to kind of throw this in the back of your mind, that says that the sum there, the Riemann sum, converges. That's another term for that limit of the Riemann sum existing there. Okay. So that is one condition for us. And then when this actually works out, when the definite integral exists, we say that f of x is integrable. That is a fun vocab word. Integrable, that means able to be integrated.